All right, let's talk about factoring, the most important thing in all of high school math. So the first thing to recognize is when you have a problem that can be factored, you've got a bunch of different ways to factor. The most basic way is the greatest common factor. What do these terms all have in common? They all have a 7 and an x, and they all have a 7x squared. So if I take out a 7x squared of this one, what am I going to be left with?
X squared.
X squared. How about for this one?
Minus
2x. How about for this one?
Plus 3.
Good. Now I have to think to myself, is there more that can be done? Can I do more to this? Can I factor this out?
Negative, you do x minus...
There's going to be not a way to do this. No, because if I wanted to put a minus 3 in here, I'd have to put a plus 1 in here, but that would give me a negative, and I want a positive. So this actually doesn't factor anymore.
That's it. So that's the answer.
So your answer is that one right there. All right, let's try this one now. Now, sometimes you have to recognize when there's a pattern. And the most common pattern is the difference of perfect squares. Remember this formula, a squared minus b squared equals a plus b times a minus b. And that's the formula that I've got right here, because this is 9x squared squared, and this is 16 squared. So I have a difference of perfect squares. That's my a, that's my b. So how does it factor? It factors into 9x squared and 9x squared plus 4 and minus 4. That's how that factors. But I'm not done, because they're tricky. What they did is they gave me problems so that this wouldn't be completely factored yet. So this right here is factored. I can't factor that. That's a sum of different squares. But notice here, now I've got 3x squared there, and I've got 2 squared here. So this is going to factor further into 3x plus 2 minus 2. That one factors more, so now let's bring this one down, which didn't factor further, just so we have our answer all in one line. And there's your answer for factoring completely that problem. And then check it. Always check to make sure it's factored. Can these be factored anymore? No. Can this be factored anymore? No.
Yeah.
Oh, notice I did make a typo right here. This right here should be 16, which means these two should be 4. Sorry about that mistake I made there. So that should be 16, and now that's 4 and 4. And none of these factor any further because we don't have difference in perfect squares. Notice this is a perfect square, 4 is, but 3x isn't, so that can't factor any further. Right. This also is 16 right here and here.
Compliments of Mark Dwyer.
Compliments of Adam Rice. Thanks, Adam. Good job. Way to go. All right, let's try one
It's
more.
going to be like me and you the only ones who could explain this one.
All right, here's another type of example. You'll have something that needs to be grouped. So what I do first is I recognize that these two things and these two things have GCFs. When I pull them out, I'm going to have a common factor left over. So let's take a look at how that works. So the GCF here is x squared. And when I pull that out, I get 5x minus 3. You got to be careful with this negative right here. I like to do this. The GCF here is, notice I've got a negative right here. So I want to take out a negative. I want to take out a negative 3 of these two, because that way it'll turn this into a positive 5x, and it'll turn this into a negative 3. And now you can see that I've got two terms, and these two terms have a factor in common, namely 5x minus 3. So I'm pulling out this GCF again is what I'm doing. 5x minus 3 is the GCF, and what's left behind when I pull that out? An x squared is left behind at the first term, and minus 3 is left behind on the second term. Now, notice this doesn't factor any further. It looks like it might, because it looks like it might be a difference of perfect squares, but it's not, because 3 is not a perfect square.
What is the difference of perfect squares? That's a stupid question.
So this is called a difference of perfect cubes. A difference, notice how that's x cubed and that's 3 cubed, right? That equals 3 cubed. So when you have a difference of perfect cubes, this is x cubed minus 3 cubed. This actually factors as well. There's a pattern. And here's how the pattern works. We use this, some teachers use this, I find it very helpful. It's called SOAP.
Oh, yep.
Oh yeah. Okay.
So this is going to be the same sign. That means same. This is going to be the opposite sign of what's right there. And this is always positive. There's your signs. And now what you do is you take this right here, and you put x there, you put 3 there, and you square it here, you square it here. See how I squared this and I squared this? And in the middle you multiply them together. So now let's check it. Let's check to make sure that that actually works. If I multiply this in here, I'm going to get x cubed plus 3x squared plus minus 9x. And if I multiply this in here, I'm going to get minus 3x squared minus 9x minus 27. And you'll notice that these will cancel each other. And something else should have canceled each other. 9 minus, did I do something wrong? This is a, oh, this was a plus 9x right here, not a minus 9x. These cancel each other, and I'm left with x cubed minus 27, which is what I started with. So that's your pattern. That's another pattern that you'll see. It's called a difference of perfect cubes, or actually it could be a sum of perfect cubes too. That's why we use the SOAP trick. If this was a plus here, the difference with this would be a plus and this would be a minus, because it's the same, opposite, always positive.